hello to everybody. We are continuing the way to measure time in the sedimentary record. We had the talk of Earth some time ago about very long-term dating with uranium lead. And now we go to a shorter range with Sébastien Nomade from the LSCE, so it's the Laboratoire of Science of Climate and Environment. And he's one of the best specialists in argon dating and focusing to high resolution measurement, very high resolution measurement. So it's all yours now. You can share your screen, Sébastien.
So hello everybody. Thank you, Jack, for the invitation to share my my research on argon dating. And I will start my presentation by thanking my colleagues Merrihue and Vincent, which are my colleagues in the Argon lab, because most of the stuff I will show you have been done with their help. So let me summarize what I will talk today about. So we'll go through an historical perspective, because I think it's important to see how fast things have changed in argon geochronology in the last 10 years. I will talk about the way we date rocks and minerals in argon, going from the decay constant, how to determine the total and parent products, the calibration and accuracy, because I think it's one of the things that are the most interesting for you guys. I will talk about the analytical approaches that we have currently. I will focus a little bit on the high sensibility multicollectors mass spectrometer that we have now since a little bit more than 10 years, that change our life and the way we do argon geochronology, but also change the precision of our measurements. And I will go through three specific examples of how this new high resolution mass spectrometer could change our life to understand and better control the duration and timing of relatively rapid climatic, environmental, but also extinction, like the KT boundary. So a little bit of history. So very soon, in the beginning of the discovery of radioactivity, the potassium have been demonstrating to be radioactive, or at least part of the potassium. And in 1935, the discovery of the potassium 40 as a radioactive isotope, then confirmed later on, have led to some publications in the late 30s about a way to use this decay constant to date rocks. Just after the war, the Second World War, had reached a near determined the first potassium argon in the University of Cambridge. This is a picture of these two amazing guys who changed our life and the way geology is have been made. And one of the main problems and the main goal in our science is to determine the radiogenic present in our rock. And to do that, we need the atmospheric composition. And this is only in the 50s that NIR determined the first atmospheric composition of the atmosphere. Rank and Koenig in 1959 proposed the first precursor of potassium of argon using counting techniques. And using potassium argon, Leakey demonstrated the antiquity of human evolutions very early in the 60s. Probably some of you don't know that, but a manuscript written in Icelandic by these guys here, Sigurd Gergesson, outlined the argon dating method before the very important work in 1966 of Merrihue and Renne Turner from UC Berkeley. Unfortunately, the paper was published after the death of Professor Merrihue in 1965 from a climbing accident. You could see here a picture of the late 60s mass spectrometer. You will see the difference with what we have right now. In the 70s, this is the first argon dating of lunar samples by Renne Turner in Science. And in 1977, one of the the main important articles that have been published for geochronology was the definition, the recommendation of the decay constant for various isotopic systems, and in particular potassium decay constant. In the 87, with the improvement of laser ablation and the precision of measurements, the first argon-argon dating on single crystal have been published, and this is what they call the defeat of xenocrystal contamination. I will show you that this xenocrystal contamination could become a problem in some cases. In 92, following the first publications on the single crystal laser fusion, the probability edge spectrum formalization by Dano and Potts also made his appearance. In 98, the first real flux standards intercalibration by Renne et al. This is here a picture of this publication. And in 2000, it was, I would say, one of the tipping points of our dating method. It's mean a collaborator questioned the accuracy of this decay constant in a paper that is now one of the most cited articles in argon-argon geochronology. In 2006, finally, after 56 years, new measurements of the atmospheric composition was proposed, which is a little bit higher than the one we used before. And in 2008, once again, a tipping point, the paper of Kuiper et al. About the synchronization rock clocks on Earth history, and this is an example of some pictures extracted from this article. In 2008, this is the main revolution of our techniques, is the first multi-collection mass spectrometer on the market. It's really a revolution. I will show you the difference between what we can do with a multi-collection mass spectrometer and what was done with a mono connection. It's a different world, in fact. In 2010, Renne et al. Proposed an optimization of the decay constant based on argon-argon random-led cross-calibration. Finally, the last paper that I would like to highlight is in 2001. In 2021, 35 authors coming from all around the world agree on a way to interpret and report argon-argon data. That was last year. So you could imagine how many things have been published since and until, and that have problems, and it could cause problems to people that are not aware about things that should be reported in articles. So the general physics behind the method is very simple. It's the potassium 40 that decay into 40 argon and 40 calcium. You could see here the abundance. This is a relatively simple equation to allow to calculate time with it's the classical one. So one of the difference between argon-argon and random lead is that in our business, we date the eruption, not the magmatic age of crystals. Why? When you are in the magmatic system, the temperature is so high that everything which decay from potassium is evaporate, is going out of our system. So the system is somehow open. But as soon as the eruption occurs and the crystals or the rock cool down below a certain temperature, the system becomes closed. And of course, at that time, the 40-36 ratio inside the rock equilibrate with the atmosphere. This is our T0. With time, of course, argon coming from the decay of potassium is trapped into the crystal matrix, and the ratio inside the rock become higher than 298.56. Of course, you have to remember that the main hypothesis that we are making is that the rock or the minerals equilibrate with the atmosphere at T0. So now, how can we determine the potassium 40 and calculate an age using the argon-argon method? So the argon-argon method is a specialized variant of potassium-argon. It means that the concentration of parent products is measured by neutron activation and not directly from the potassium concentration. How do we do that? We take our samples and the sample is irradiated in a fast neutron reactor. This induces a neutron capture and a transformation of 39 potassium into 39 argon. The products have an half-life which is relatively long of 269 years. We know on Earth the abundance of potassium is constant. So by measuring the 39, we could go back to the 40 potassium. Okay? However, it's impossible to determine the quantity and the concentration of 39 that have been produced directly. So in 1968, Mitchell defined the quantity J, which is the flux factor. J is determined by analyzing materials of known age. That's our standard. It's the J value. So J is equivalent to these equations. You could recognize the same equation I just showed you, but rearrange a little bit. So we measure 39 argon coming from the potassium and the 40 argon radiogenic in these materials of known age that we co-irradiated with our sample. And we simply re-inject this J value inside the age equation that we have here. And to obtain an age, we measure in the same condition the 40 argon potassium, 40 argon radiogenic into our unknown. Of course, as we irradiate samples, we cause problem to our measurements. First of all, in the nuclear reactor, the neutron flux is not homogeneous, especially. So we have to monitor these variations. So we use specific design, like this one here. So in each disk, we could put 5 or 6 samples, and around these samples, we have standards. Okay, so we could vertically and horizontally check the homogeneity of the quantity of neutron. The variations inside a shuttle is about 0.1 to 0.5% vertically and horizontally. But this largely depends on the irradiation duration. We use rotating tubes, so we could homogenize this J value. So for each age we provided, for each sample, we have at least 3 standards measured at the same time. This is a minimum. Usually we measure 6 and sometimes 9 if we want to have a better precision. During the irradiation, we also create other argon isotopes, some other products like calcium, for instance. Some reactions are, let's say, positive for us because it's allowed us to give information about the potassium-calcium ratio in our samples, and some of them are problematic. So we have to correct them. So for that, we irradiate our samples in a cadmium shielding tubes that reduce some of this reaction. And we irradiate also pure material rich in chlorine and potassium and calcium. It's the so-called salt corrections. And of course, the importance of this correction it depends on the chemical composition of our samples. So the more calcium you will have in your sample, the less precise your edge will be, because you will have to correct for this uncertainty. That's why basalts, that's why plagioclase will never be as precise as potassic feldspar. The last but not the least problem is the fact that as we irradiate with high energy neutrons, the 39 that we produce have a residual kinetic energy that have been transferred by the very energetic neutron. So, in fact, this kinetic energy is lost by the 39 argon by an energy of ejection. So Fermion argon produced by potassium could recoil as far as 3 micrometers, but the 37 argon from the calcium 3 times the distance. So it means that minerals too small or with high volume to surface ratio can produce conspicuous older edges like micas, clays, but also small crystals smaller than 30 microns. You cannot really date, or you have to think about an experimental chems that are specific. You cannot date small minerals with argon. Furthermore, if you look in the literature, I will say over the last 50 years, you have 3 decay constants that are used. That will produce an age which is different. We have, of course, the Steiger-Jaeger, but it is not used since now a few years. You have the mean etal and you have the Renne etal calibration. So this one is the original one. There is no uncertainty recommended. This one of mean etal is a critical reevaluation of the Steiger-Jaeger activation data. And this one is a statistical optimization based on 16 pairs of random lead and argon-argon edges. So you might ask the question, what is the best calibration? Of course, mean etal is more accurate because you have an uncertainty. So it left us with 2 possibilities, the Renne etal and the mean etal. The calibration of Renne etal will incorporate diverse physical measurements. And of course, you have a quantifiable uncertainties. The other one here is based on astronomical correlation following Kuiper et al. That I will talk a little bit later. But there is no absolute uncertainties on that one. Okay, so I will not choose. It's a question of what you want to do. You want to be independent or not of astrochronology. Of course, there is a lot of recent works thanks to high resolution mass spectrometer that led to improvements on the precision and accuracy of standards. So I listed here a list of standards with their recommended age according to mean etal or Renne etal. You will see the difference that it could make for a standard that is 1.2 million years, 28. It could be several millions of years for a billion-year-old rock. Okay. So for many people, the standards, the uncertainty on the standards and the accuracy of these standards is one of the Achilles tendons of argon. But in fact, it's not fair. It's not fair because it's easy to recalculate an age based on any given standard to an age based on another standard. So anybody can do that. Of course, the problem is in many publications, there is no such information in the articles. They will not give you the age of the standard they use. So you cannot recalculate. That's one of the problems. And of course, standards are used only to determine the parent isotope, as I showed you. So the argon-argon method is no more relative than other methods that using tracers that are dependent to the tracers they use, uranium thorium and uranium lead included. Talking about the calibration and accuracy, this is a nice figure that I took from Shaen et al. In the GSA bulletin. As you could see, no matter the age or the composition, the main problem is the 36 argon measurements. This is the current limit of our analytical precision. This is the blue here. So the ability to measure accurately and precisely the 36 beam, and especially small beams, could be achieved only using the last technological advances in ion counting technology. Of course, the other limiting parameters is the capacity to discriminate 36 argon from mass interference, chlorine, hydrocarbon, which once again is only achievable using state-of-the-art spectrometers and also specific cleanup procedures. So to summarize everything, the accuracy of the argon-argon method is based on 3 components. The first one is the argon isotope measurement itself. So with all the corrections and background concentration, mass biases, which are non-systematic. And now I could say, and I would not have said that 10 years ago, we could do better than 0.2%, and usually less with potassium-rich materials. The second corresponds to the operation required to obtain all the other argons coming from the neutron activations and the radiogenic. Of course, they depend on the sample composition, and this is the main source of uncertainty for the calcium-rich minerals. That could be up to 10% for tolite, for instance. The last limit will be the accuracy of the argon-argon, come from, of course, the age and standards you use and the decay constant you choose. And of course, depending on the calibration you choose, let's say the more precise and I would say accurate decay constant is given at 0.36% by Renne. If you take, for instance, Minetal, the error is up to 3%, the uncertainty that you have to propagate. So if you compare rhenium lead with argon-argon, you have to include this uncertainty. It's usually never done. So the component 1 or 2 that I listed here are analytical or intra-laboratory uncertainties. They are complex to evaluate, and because there is a lot of error correlation that you have to take into account. If you include component 3, this one is systematic, and or intra-laboratories uncertainties. And more it's common to report both intra and extra laboratories uncertainty, this way, for instance. So this is what I wanted to show you. It's what could have been done 10 years ago and what we could do now with multi-collection mass spectrometer. The precision in red here and in gray compares measurements made on the same samples with a monoconnection machine and with a multi-collector mass spectrometers. For instance, this is mesostase. This is for mesostase, of course. This is for cyanidine. For instance, it's cyanidine which are relatively close from the loose material boundary. You could see the difference between a machine that is a great machine, but you could see the precision that you have, which is about 3 times better with a multi-collection mass spectrometer. This is another example with biotite, for instance. Once again, the potassium feldspar, lucite, and cyanidine remains the preferential material for high precision argon-argon geochronology. I will not try to do high precision geochronology with basals or with plagioclase. It will be a disaster because of all the correction I just showed you. The internal uncertainty can reach now 0.1% with this kind of material. This is another example with a standard that is well known because I published this in 2005. In 2005, yes, you could see the difference between here machines which are monocollector mass spectrometers and what we could do through the age from 2011 to 2020 on the same standards, which is Fish Canyon in that case. You could see the difference. This is monoconnection. This is multi-connection mass spectrometer. This is for 28. It is for 1.2 million years old Alder Creek. This is the example, but you could do the same for Fish Canyon. This is an example of what has been done in 2011, and this is what right now we can do with single crystal dating at 28.2 million. And this is, I just want to show you to compare argon-argon dating here and rhenium lead dating on the same ignimbrite, which is the Fish Canyon. You could see the spread of ages on the zircons, which is the effect of resident time. If you remember the presentation of Urs, and in fact, there's only 3 crystals here that fit with the argon-argon ages. 3. All the rest is affected by residence time or other problems of dating. But as you could see, the uncertainty, individual uncertainty of monocrystals of cyanidine is as good as uranium lead. And we can measure much more crystals than uranium lead. So the analytical approach, with two big groups of analytical approach. You could do step heating method on mesostates, on mineral population, on single crystals. It's a long process because you have the irradiation phases that takes up to 2 or 3 months. You have gas purification, you measure with mass spectrometer, and you end up with two different kind of way to present the results. The first of all is the fact that with argon-argon, you have the ability to release argon incrementally. Since the 70s, H spectrum have become the standard to depict this kind of step heating. So what you have here, it's each step corresponds to a temperature, and you have an increasing temperature here. So individual steps are model age. It means that they are calculating with T0 atmospheric composition of the rock. With enough continuous step that have the same age within uncertainty, we call that concordant spectrum. And if they share indistinguishable ages, it's a plateau age. Of course, most of the spectrum are discordant. They are not concordant, and they're called discordant. This is some examples that I take. And some spectra occur frequently enough to be to make categories. You have the plateau age concordant spectrum. You have discordant. This is due to argon diffusion. You have other ones that show a redistribution of the argons inside a crystalline matrix, and you have discordant spectrum due to excess argon, for instance. So all these kind of spectrum could be found, and you could find all the intermediate between them. Of course, some information into the cause of this discordance could arise from casting step heating into isotope correlation diagrams. So they are bivariate diagrams. Most of the time we use inverse isochrone. So the inverse isochrone is a way to present, in fact, the data. Each of these points is a step, and the y-axis, in fact, is the inverse of the 40-36, the initial ones. So this is equivalent to T0. And this is here, the intercept that is proportional to the age. That's a 39-40 ratio. So let me explain to you, how do we build that? If the intercept here is atmospheric, everything is okay. If the intercept is not, we know that there is excess argon, but we could still give an age. How do we build that? It's relatively easy, in fact. This is ideal spectrum that show excess argon. So from step A to J in the spectrum H model are based on air correction. So this point here, this is the atmospheric correction. So graphically, they correspond to the projection through this atmospheric to this line. Okay. So this is how we transfer this kind of measurement to this one. If all the points align between an atmospheric component and radiation component.
Sébastien, can you relate in a more explicit way the line to the left diagram?
The line.
I'm a little bit lost here. Ah,
okay. So the point here is the low temperature, and the low temperature is this point here. This point here is the point here. It's just if at T0, at the moment of crystallization, the rock equilibrates with the atmosphere, you have an isochrone that is a simple mixture between the atmospheric component, the 40-36 ratio, and the 39-40 ratio, which is let's say the radiogenic component. Okay. But if you have excess argon, everything is shifted, and the first point do not correspond to the atmospheric. So how to build from there to there is a simple projection from an ideal case to the real measurements, that is a 30-36 ratio in that particular step. Okay. Let me show you here, for instance, this is the radiogenic pole, this is the atmospheric pole. If everything is aligned in a perfect way, you always have a 40-36 ratio initial intercept that is atmospheric. But in some case, the rock is not equilibrated with the atmosphere. So we could control if at T0 our rock or minerals have been equilibrated with the atmosphere. It's just a way to control things. And you always have to control these things. I will show you another example. So you could do single crystal fusion. So the same way, the same process. But in that case, you measure grain by grains by laser ablation. And in that case, you use probability diagrams. I will come back to the isotopes just after that. So individual age are treated assuming a Gaussian distribution. A single age for this population here, the youngest one, is calculated by the weighted mean. And of course, what you have here, it's where to account of the variability of each individual analysis, the imprecision of the age affects the weighted mean the less. What it means to calculate an individual age from that, you don't take into account only the analytical uncertainty. Because the scatter that you have here is consistent with the analytical uncertainties. For testing if the population is homogeneous with a meaningful MSWD, the systematic uncertainty must be ignored. So it should be added at the end. This is another example. And as you can see, an age calculated based on statistical homogeneous population is also an apparent age because each of these age is calculated using a 40-36 ratio that is atmospheric. So once again, you have to control this hypothesis using an inverse isochrone. As you could see, all these grains align, and the intercept that you obtain here is an atmospheric within uncertainty. Okay? So what I mean by everything I showed you is the fact that argon take times between sampling, preparing, irradiations, measurements, interpretation. You cannot have an argon age in less than 3 months. I would say a year is the usual. You could apply these techniques to various lots of materials that have different temperature of closure that allow you to do thermochronology. I will not talk about thermochronology today, but there is a lot of material that are appropriate for argon geochronology. Let's move to some consideration about the high sensibility multicollector mass spectrometer. This is 3 examples of commercial mass spectrometer that are now on the market. You have from isotopics, new instruments, or from thermo, and all of them have multi-connection arrays that are high sensibility, laser fusion, and they are fully automatized. It means that they could measure a lot of crystals. This is some examples of ultra-compact purification light that have only 500 cc's. This is our system. This is an example of the way some isotopes can affect the concentration of 36. This is an example that I take in GISHA, where you see the 36 peak, which is not made only of argon, but of other species. An high-resolution mass spectrometer with power of separation between the mass could allow you to reduce the impact of this contaminant on your 36 measurement. And as I showed you, the 36 measurement is the main problem for our precision. This is an example of the blank to an individual very small 500 microns cyanidine, which is very young. So this is the beam of 40 that we measure, and this is the blank that we have. This is an example for a Faraday Atona cup in our lab. And one of the power of these machines is that they are very stable in terms of 40-36 ratio for the mass bias corrections, and also to calculate the quantity of radiogenic potassium, radiogenic argon. So very stable. You can measure very small and precisely small beams. So it's really a revolution for us. Let me show you how we are capable of doing right now. This is an example of the Napolitan yellow tuff. So this is a big eruption from the Campi Flegrei, and this is the zone of deposition of this huge eruption, the Napolitan yellow tuff. And in 2004, an argon age was published by Aldeino. Just as a reference, the current age for this eruption is given by C14. This, you could see the uncertainty at 2 sigma. The valve age is known from a lake. This is what was produced using a single collector analogical detectors in 2004. This is single crystal, 1 millimeter measurements. And at the time, you could see that you have an error which is relatively good, but we do the same sample with our machine, same grain size. You could see that this was made of two populations of crystals, one at 20,000 and one which is at the age, expected age for this Napolitan yellow tuff. And we have a precision which is better than the C14 and better than the valve age. This is 40.1 kiloyears eruption. There is only 20 years of difference between these two. In terms of technology, I mean. So we could do things that are that were not possible 5 years ago with these machines. Let me give you some examples of what we've done in the last 3 or 4 years on the high resolution chronology of some of very important markers in the Earth history and in the quaternary, more particularly. So I will first talk about tektites. So why tektites? So tektites are formed by a large meteoritic impact, more than 10 kilometer craters. They correspond to melted ejecta of the target rocks. So you could see we know their shapes, how far they go as a function of the impactors. This is some examples of pictures of macroscopic tektites from both in China. And this is a picture that I took from a core from the China Sea. And you have micro tektites here that are very, very nice and relatively small, but easy to find. So the Australasian true field is the biggest, in fact, true field in Earth. It covers 20% of the Earth's surface. It means that below this umbrella, you find these tektites. Until 2017, the age was imprecise, around 800, I would say. It was what you find, in fact, in the literature, but more precisely between 760 and 820 kiloyears. The paleoclimatic group knew since a long time that microtektite peaks in marine core were always found at the T9 terminations between the cold period MS20 and the warm period MS19. Therefore, for all the cores and all the records you have below this umbrella, it's a very powerful correlation tool if it's precisely and accurately dated. Of course, climatostratigraphically, as it is in the termination 9, the age was estimated between 795 and 785 kiloyears. Can we do better? In 2017, Mark et al. Proposed an age based on the 2 tephra layers bracketing this, the tektite layers in this core between at 786 kiloyears. Of course, it's not a direct age. So in 2019, with my colleague Aldeino and Fred Jourdan, we collected new tektites in 4 countries and analyzed them in 3 different laboratories, in Curtin, in Australia, at the BGC, Berkeley, and here. And we end up with a more precise and accurate age of 788.1 plus minus 2.8. I just wanted to show you the precision of the measurement that were made by multi-collection mass spectrometers in Curtin. This is individual, small 100 milligram quantity of this tektite. So this is very important because now we could correlate all the paleoclimatic records below this umbrella of tektite deposits, covering 20% of the Earth's surface. More recently, my colleague Pierre Rochette published 2 articles. We are part of this group that studied the Pantasma crater and the Belezite tektite. Both have the same age by Argon. So this is the fifth couple impact and through field discovered on Earth. The age is 804 plus minus 9 kiloyears. Why it is important? Because it means that there is 2 different impacts in less than 10 kiloyears that create a through field. And these 2 were equatorial. For a long time, Belezite have been believed to be related to the Australian through field, but it's not the case. There is another impact, which is nearby, the Pantasma crater. They share the same composition and the same age. But we proved that only thanks to a multi-collection mass spectrometer last year. Let's move to something which is slightly younger, and I will talk about the MS19 log centricity interglacial. I'm pretty sure you know that, but I will say that again. The age model of almost all quaternary published paleoclimatic records beyond C14, and excluding of course Peloton that could be dated by thorium up to 640 kiloyears, are primarily based on astrochronology. So they rest on simple alignment to a reference target. They assume constant leads and lags between proxies and orbital forcing. In 2016, Lizeki and Remo said, simple alignment targets neglect regional differences of several thousands of years in the timing of benthic delta 18 changes during glacial termination, for instance. So what I mean by that is our understanding of the spatial and temporal variability, magnitude, regional expression, and underlying mechanism of past climate change depends on high quality, high resolution proxy series. But of course, they need to be anchored into independent, accurate timescale in order to avoid circular reasoning, which is the common problem in high-resolution quaternary climatic research. So our current interglacial, which is the Holocene, have a specific orbital forcing parameter that is found 3 times, or at least close, 3 times over the last million years. So the study of high-resolution interglacial, past high-resolution interglacial, is one of the ways to understand the natural variability of our climatic system without human activities. So of course, MES11 and MES19 have been studied heavily over the last 20 years for this specific reason, understand the relation between climate forcing and our current climate. This is an example of work that have been done more than 10 years ago by Cathy Paul and Kronis Zedakis, showing how, in fact, the 2 periods, the Holocene and the MS19, are similar in terms of orbital solution, but also climatic evolutions. So you have in blue here the MS19, and of course, we have the Holocene that is in green. So we have different records that have been here synchronized, but they have been synchronized only from the climato-stratigraphic point of view. We don't know if it's true, if they are aligned the same way and they react the same way to the climate forcing, because all of these records have been dated using astrochronology. So by assuming a constant phase or lags between climatic proxies and orbital forcing. So can we do better? And in fact, it's one of the goals of several projects that we've done over the last 10 years. in Italian peninsula. There is 2 exceptional records with high resolution and, more importantly, with interstratified tephra layers that can be precisely dated by argon-argon. So since 10 years, we studied these 2 records, which are high-resolution MES19 records. Let me show you the first one, which is the Sumona Paleo Lake. So it's a lake located in central Italy, in one of the basin range of the Apennine Mountains. So this is one of the sections we studied. So you could see the tephra layers. This is relatively homogeneous, carbonaceous, very fine-grained carbonates. So this is examples of other sections here. And we were able to build a stratigraphy, a complete stratigraphy covering the entire MES20, MES19, and MES19. So this is what we published in 2015. This is the first publication that we've done on this particular record, which is a 150 years resolution of hydrological variation about the Apennine, with all these independent argon-argon edges to control the age, which allowed us, in fact, to construct this independent chronology that we compared the time with EDC and with the high latitude marine sediments core. And we soon realized that there is problems, because you could see these millennium oscillations at the end of MES19. They are not the same duration, are not synchronous. And so all these records cannot be correlated each other. The only one which is independent is this one. What we saw also is the fact that the interglacial, I mean, paleoenvironmentally speaking, started just before the maximum of precession. These ones have been constructed based on the fact that the maximum insolation should coincide with the maximum in terms of temperature here of surface. So that's why they are aligned with the maximum centricity. We did not find this in our record. We continue to work on that record, and in 2019 we published this decennial records of variability during MES19 based on more chronological control, and we highlighted during MES19 a 5 to 6 kiloyears cycle, which corresponds to the 4th precession harmonic. We demonstrated that during this period you also have an equivalent to the 8.2 kiloyears event, and we're still working on that particular record, especially for the terminations. And we recently acquired 3 new argon-argon edges, high-resolution argon-argon edges, that will allow us to present a revised chronology for these records. We also have another additional data that I will just show you after, that allowed to use this particular record to how could I say that without being too that allowed us to recalibrate all the chronology for the entire MES19 records worldwide. The other record is an expanded marine section with high resolution sedimentation rates, which is about 95 centimeters by kilo year. This is the example. This is the section itself. So it is a marine sequence. You could see here this white layer here. It's a tephra layer. You see another one here. So this record has been studied since 20 years, and in 2019 I published a paper focused on that particular section here. That includes 2 tephra layers and span MES20 to MES19 down to MES18. So I will not go into too much detail on this record, but
sorry.
But you could see the same oscillations at the end of MES19 that the one which we show in the Sumona Lake. And one thing that we have also here is we have barium 10 measurements. So barium 10 is very important because that's the signature of the Bruns-Matuyama boundary. The V4 is very important because it's found at the end of this barium peak overproduction, which is the Bruns-Mathieu. So the age of these tephra layers have been measured countless times now in BGC here, University of Wisconsin. We found, in fact, the origin of these tephra layers, which is the Faraday-Olivo ignimbrite, which allowed us to measure with our new machines with a better precision the age of this tephra layer, which is the only one tephra layers with potassium feldspar that is within the Bruns-Mathieu boundary. All the rest, all the data you have are based on basals, and I show you how basal could be a problem with calcium correction. So now, why I told you about the barium production is that the production of cosmogenic nuclide in the upper atmosphere, and of course barium, is modulated by the strength of the Earth dipole magnetic field. When the dipole collapses, the production in high altitude of barium is increased, and the barium is very heavy, so it is trapped into the go down into the atmosphere and run into the soil and the sea very rapidly in a matter of years. So this is a way, in fact, to reconstruct the variation of the Earth magnetic field through time by measuring the barium-10 inside sediments sequence. So this is what my colleague Quentin Simon did in 2016. He just created a stack of barium productions from 850 to the present day. And you could see here this overproduction. This is a multiplication by 2 of the production of barium-10 into the sediments due to the Bruns-Mathieu. He did this kind of measurements in various cores, marine cores. We could do the same thing, and it has been done in early 2010 in Epicadom Sea. You could see the Bruns-Mathieu as seen by the barium peak here. We've done that in Montalbano Iochimico with this peak here. That is dated by Argon. This is the age that you have here. It means that the Bruns-Mathieu, first of all, 2 things. The Bruns-Mathieu is not instantaneous. The collapse and the recovery of the dipole field takes time, in fact. Of course, you could see that depending on the sedimentation rate of the records, the peak is large or small. And in fact, it is small in high resolution record, and it is large and long in low resolution records. This is a sedimentary bias. Everything is stretched by the effect of post-depositional bioturbations. So the highest resolution you have, the narrowest is the barium peak. Why I say that? Because now that I showed you the Sumona records with its independent chronology, we have now a barium production curve for this record that is fully independent. Epicadom Sea have also a barium-10 data. The Shiba, which is the GSSP section for this period, have also a barium peak and a nice paleoclimatic records. Montalbano Iochimico, as I showed you, this is a marine record. We have also now barium-10 records. If you put all these records in their own chronology, this is our independent chronology based on Argon. This is an independent, semi-independent chronology that is tied to V4 for the peak of barium. And the Chiba section chronology is solely based on, let's say, astrochronology, but not direct astrochronology. It's tied to the Zekier-Remo stack. Okay. And the chronology here, as Epicadom says, it's at the bottom of the core. So there is lots of things that could produce bizarre things in isotopes. And the uncertainty of the record that is reported in the last Epicadom Sea chronology is plus minus 5 kiloyears. Each point have an uncertainty of 0.5 kiloyears. So what I want to show you with this particular figure is the collapse of the dipole field related to the Brunns-Mathiama is synchronous worldwide. And the duration should be the same in all records. What this record showed, it's not the case. But why it is not the case? It's because they have chronology which are not accurate, especially the Chiba. You have a duration of the peak production of barium, which is twice what we have here in Sumona, and 3 times what we have in Montalbano-Ionico. So what I mean is the fact that the end of the production, of overproduction, should be synchronous in all these records. If you do that and just draw a line across this edge, which is well constrained by this argon-argon edge, this is where it should be in every record. You could see there is a difference of 10 kiloyears here, or 5 kiloyears here. So what's happened if now we assume that it should be synchronous, so we shift all these records to have an homogeneous end for the barium peak. So just do that. We do that. This is what we obtain. So the duration is the same. The climatostratigraphic position of the end of the barium peak production is the same. During the first oscillation at the beginning of this first oscillation, warm oscillation at the end of MES 19, in all records. What you could see is that the Brunns-Mathiama duration is homogeneous within uncertainty in all these records. It's about 10 kiloyears. And all the independent edges on the Brunns-Mathiama fall into this period. This is for basalt dating. This is based on the dates from North Atlantic deep sea core. And this is the edge we obtain in Montalbano-Ionico for the V4. I just put you here the edge of the Australasian tektite that are in all records 20% of the Earth's surface at the transition between MES 20 and MES 19. And if you look at Lidzeki-RMO, this is not in the transition. So it means if you tie any record to Lidzeki-RMO, this is wrong. The chronology is wrong. So let's go through rapidly the KT boundary for time. So in the early 90s, the argon-argon have been used to date the KT, and especially using the Belloc tektites that are found in Wyoming or in here, I don't remember, in Haiti. So the edge that were produced at the time goes all into the direction of 65 million years. And in 2008, of course, the work of Kuiper on have changed the edge by changing the edge of the Fish Canyon Sanidine. And by looking at the Sumaya section, the KT boundary should be 1 million years old earlier than the argon-argon. But by using the Fish Canyon Sanidine and the Min et al. And recalculating the edge already published, Kuiper arrived to edges that are pretty much the same that the astronomical solution. In 2013, Renne et al. Dated a bunch of coal deposits that were rich in volcanic materials by argon-argon. This is here. And this is the random lead edges that have been done in the same units. You will see here is a spread. It's not that much minerals, but they all correspond with velocity to the mean of the sanidine edge that have been measured. These are other examples of the quantity of measurement that could be used to date a particular bentonite layers, which is to compare with zircon chronology. Of course, in 2013, they redate the beloctite, and once again, by recalculating the published dates on using the new decay constant and the fish canyon sanding at 2802, they find the same age, which is good. Meaning, once again, you could always calculate an argon-argon age with another standard, which is good. In 2016, in Clyde, using the Denver Basin, produced an age for the KT boundary between two random layers, which is compatible with the one I just showed you. Sprain in 2018 produced also argon-argon ages that point toward an age which is compatible with random lead of the KT boundary. So everything seems to be okay. But I don't know if you, I think that Urs showed you that. I'm almost finished. This is what I told you for calcium-rich materials. So this is the ages, the comparison between random lead ages on the Deccan trap and argon-argon ages. So in blue, you have here the argon-argon ages that have been produced by the group in Berkeley. And this is the uranium lead edges that have been produced by the group of Shaen. You could see that in the case of argon-argon, you have huge uncertainties. This is solely due to calcium correction. The random lead seems to indicate very pulse of volcanism. This is the argon-argon age produced by Sprain on the Elk Creek. This is the uranium lead of the KT on the Denver Basin. So everything seems to be concentrated here. Of course, you have less precision for the argon-argon. So everything seems to be okay, despite the fact that you have a huge uncertainty for argon-argon, which is normal, it's calcium correction. But there is another figure in Shaen et al. That shows the effect of the standards you use and the age of the standards. So this is a figure where you have here the uranium lead dating on the Fish Canyon. And this is the different estimates, argon-argon estimates for the Fish Canyon. As you could see, the Renne et al. One seems to be a little bit older than the uranium lead age. These figures have been made using the Renne et al. 2011. But if you change the decay constant and if you change the Fish Canyon age, this is what you produce. You shift everything into the younger age for argon-argon, and the two chronometers are completely off each other. So this is a problem. So where is the truth? I would say that both of them within uncertainty agree. So there's still this problem. What is the age of Fish Canyon? I don't know. So this is the take-home messages that I would like to share with you. So methodological and technological progresses allowed to obtain now argon-argon age and potassium feldspar from lower Pleistocene to Archean with internal uncertainty which are better than 2%, 0.2%. Of course, standards are used only to determine the parent product. So the argon-argon method is no more a relative dating technique than other methods using tracers. The absolute precision is limited by the total decay constant uncertainty. That remains the problem to be solved because, and also the interference collection that do not allow us to have high precision calcium-rich material dating. Argon-argon produces ages that are as precise and as accurate as random lead when resident times become a problem. And of course, and this is my last warning, the choice of both decay constant and flux monitor ages matters when you deal with ultra high precision stratigraphy. However, it is easy to recalculate an age based on any given standard to an age based to another standard. Thank you.
Okay, thanks a lot, Sébastien, for this review and these new results. And we can open for the question. I'm looking, please raise your hand if you have any.
You want me to stop to share my screen?
Yes, maybe, but there may be question on the on some of the slides. Mm-hmm. But of course, I don't see the people when so they need to raise hand in the small hand in the. Yes, yes, of course.
I knew that.
Oh, thank you, Sebastien. There was one slide you were very correctly the first time mentioning the problem, the main problem of uranium lead dating, that we have the problem of residence. So we can only we have to focus and concentrate on the youngest zircons. But in this same diagram, we also showed that the single, I think it was single grain total fusion sanidine H's, they also have a spread. And you
they have a spread, yes. They have a spread.
Comment on this?
Yes, there is a spread, in fact, and this spread could be due to many things, but it's mainly due to the fact that we measure sometimes hundreds of grains, and there is a certain variability in the natural variability that we cannot solve, and sometimes it's a continuous spread. So where do you stop? If you have a Gaussian, if you have more than 100 grains, you could always say that if I have a Gaussian repartition, so the mean is okay. But when you have 5, 6, or 7 grains and you have a spread like that, sometimes it's difficult to say anything about the age. And this is what bothers me with random lead. Sometimes it's based on 2 crystals. So statistically, it's poor. And we see that sometimes we measure 10 grains that all have the same age, and we measure another one and is younger, or we measure 10 grains that are very very different in age, and the 5 next give you a very nice population. So,
but I think this is a big discussion in the community, especially the mathematic community. Is there a natural age variation? That means is there residence of sanidine crystals in not so hot melt anymore, so which produces a real span of ages, or is it?
We are at the point where we could ask the question: do we have we have the resolution to see that? Yeah,
that would be very interesting. Okay,
there's some examples. Some examples of very big sanidine which have cores.
Maybe I don't know. You want to show, if you want to show the slide in question, maybe you should.
I think it's this one, no?
Like that, it's better.
Yeah. This one, you have all these grains which are clearly older, but from there to there, within uncertainty, they are all the same age. Statistically, you cannot discard one more than another one. Same thing here. There is clearly these 3 which are older. These few grains which are younger, but you find the same kind of spread in uranium lead. Yeah. But there is much more crystals here. So statistically, it's more robust, I would say.
Yeah, sure. Okay, I have to leave you. I'm in another seminar. I jumped out, so I just came to visit you. So thank you very much.
Thanks.
Bye-bye to everybody.
Linda.
Hello. Hi, how are you? That was an excellent talk. Thank you so much. So I have, my familiarity is with the zircon uranium lead dating, and the community has set up a number of preliminary processes, screening techniques based on the petrography or of the internal structure of minerals. Do sanidines have similar? Is there similar opportunities for sanidines, or are they too small?
No, because sanidines are really simple compared to zircons. Zircons could have could be zoned, could be growth for several hundreds of years. Usually sanidines, and the one we measure are relatively small, they could be pieces of larger crystals. They could be monocrystals. We don't really know, and they are not zoned usually. They are very homogeneous in terms of composition. Sometimes they have fractures that could explain the fact that some have less radiogenic than others. But visually, I mean, you cannot really do anything, and petrologically, nothing too. It's very difficult. Of course, visually, you could see some that have inclusions in it. So we don't usually let them. They could have small glass inclusions. But this one are removed through the process of sampling picking, of mineral picking. We work at high resolution binocular, and so the grains we measure don't have any visual defects.
So what about these older grains that you were showing in this?
Oh, these older grains. So yeah. So these older grains are clearly older. When I mean it's statistical.
Is there any?
So it's common, and I showed you here. This is common in highly explosive volcanoes that during the ascent of the magmas or just before the eruption, pieces of the host volcano fall into the magmatic chamber or are taken in the middle of the plume, and most of the big nandrites have xenocryst. This is the examples here. There is 4 xenocryst here, which are clearly older. But we could see that only because we have the resolution, the precision now to exclude them, but they were included here. So I have no idea in this kind of cases where it's so old, if these ones are really xenocryst or not. Do they need to be excluded? I don't know.
Well, thank you so much. So about the reactors that you use,
yes.
As reactors become retired, what's going to happen? Are you going to try to keep one going?
So the one we use right now in France is in the United States. Okay. Every reactor where we could do, it's sad to say because we have the biggest, the largest number of nuclear reactors in France. None of them have the capacity to do the kind of stuff we want.
Which one?
The last one closed 1 kilometer from here in 2016. So I would say right now there is maybe 5 or 10 reactors that are capable of doing neutron activation for argon worldwide. And I would say that 70% use the same reactor in Oregon State.
Excuse me?
It's very important for our community to keep this capacity, of course.
What was the facility in France that was used?
It was Osiris reactor in Saclay.
So this reactor is a neutron source. What is it?
The reactor closed. Simply.
What is what kind of reactor is it?
It's usually small reactors, research reactors, which are less than 1 megawatt or 10 megawatts. They are very small. I would say they are not dangerous, these ones, but that's the one they close.
But you use them as a source of neutron?
Yes, until 2016, until it closed. We were the last one to use it, in fact.
But is there any neutron source developed in the framework of ITER?
Yes, there is some neutron source, alternative ones, but right now none of them have the flux we need. Or we will have to let our samples for years in front of this neutron cannon to be able to measure enough 39.
Okay. Have you other questions?
Thank you so much. Thank you.
You're welcome.
We have to leave, so thank you again very much, and we'll see you soon.
I have a question about the Fish Canyon measurement, because I don't understand, because you show at the beginning of one of your slides, the evolution of the measurement of the fish canyon.
Yes.
And I'm a little bit confused now. Can you go back to this slide, which you showed a little bit before?
Yes. I think it's.
Yeah, this
here.
one. The second one. Yes.
Yeah, this one. Yes.
So we don't see it now. Yeah, this one.
It seems to be coherent, yes.
So the measurement in red, what are they? They are made with what? With which indicator?
With cyanidine.
So these are argon.
Yes. But this one have been calibrated using Kuiper et al.
They are calibrated using that.
Yes.
So
And this
they are
one.
not, you see, I was wondering why. So this is not an independent measurement.
No, it is not. It is not an independent measurement. That's my point. If you use Kuiper et al, you need to use mean et al, and mean et al decay constant may be wrong.
Okay. So you show the correlation between two things, which is
Yes.
the fish canyon measurement of Kuiper et al and the constant of mean.
Yes, but if you use Renne et al constant, you have to use another age for fish canyon, and you find an older age.
Okay. So
which seems to produce in basalts of the decant the same age than uranium lead, but using Kuiper et al and mean et al on basalts, you find a difference between uranium lead and argon.
Yes, so this is so now I understand better your conclusion at the end,
yes.
Showing that you had some discrepancy between the uranium lead measurement and the argon measurement.
Yes, but this becomes sensitive when you deal with things that have more than 10, 20 million years old. The difference by using Kuiper and mean and Renne et al decay constant and Renne et al age for fish canyon or adult creek become negligible for quaternary rocks and minerals.
Yeah,
because that's only 0.2, 0.3%. But that become very big when you go to things that are in the Mesozoic time.
Okay, so what would be the way now to get a better certainty, a better agreement, some better data for the KP boundary?
I would say that we need to better constrain the total decay constant of potassium. So let's talk about that to physicians, but it's very difficult to do. I have some ideas how to do that with natural samples, but it will take time.
So the main problem is the decay constant. It's not the sampling, it's not the analysis, it's not this. No. You show that you can do it very accurately. You can do the measurement accurately.
Yes.
I have a question about trying to use plagioclase and basalts that are, say, 200 million years old, and which exhibit some potential open system behavior or even metasomatism. Can you comment on that?
I would say that I will be very cautious on the precision and accuracy of everything which have been done on basalts. You produce ages that have uncertainty so big that comparing this with uranium lead right now, it's not possible.
Is there hope of progress?
What?
Is there hope of progress?
No, as I showed you, calcium correction will always be there as soon as you irradiate your samples in a nuclear reactor. You have to find potassium-rich minerals, differentiated horizons that allowed you to do random lead or dating potassium-rich phases. And here you have precision that are as good as uranium lead.
So maybe the same gabbroids that produce the uranium lead.
I don't know. Urs is not here to to discuss that. But one point is important here. is the fact for many problems in terms of stratigraphy, chronostratigraphy, you don't really care about the accuracy of your age. What is important is the duration of processes, duration of periods. And no matter if you use Renne or Kuiper, if all the data you produce in a sequence are made with the same standards, are made with the same decay constant, and the precision is here, the duration you produce will not change if you change the standards or the decay constant.
Yes, but you mean that you should have a decay constant for uranium lead that is in agreement with the decay constant of argon, but they will give an agreement only for one data.
It doesn't matter. The duration will not be affected by the decay constant. The decay constant is something that you had at the end. That's an external error. The internal error is good enough to produce duration on the stratigraphic sequence, which are as good as accurate as uranium lead. It's a difference between precision and accuracy. Even if you don't have the accuracy of uranium lead, you will have the precision on the duration processes. If you want to relate an impact or an extinction with a natural processes, you need to have both with the same system. You need to have both with the better accuracy as possible to link the two. But if you deal with durations of processes, I would say that the decay constant or the standard you use is not really important.
Of course, if we could count backwards in 400K cycles from the present to the early Mesozoic, we could solve that problem.
I don't think right now we could discuss about the 100 kiloyears cycles with uranium lead or argon for Mesozoic time scale. We don't have the resolution to do that, the precision to do that.
No, but I meant if you had continuous stratigraphic records.
Yes.
Yes.
Yes, of course. Okay. But if you know one, go ahead.
No, I'm muting.
We will thank you again, Sébastien. And the next talk will be so it will be back to plate tectonic and by Alessandro Forte.